Lesson 10, Distribution Table. Example 3. Use the age data, question 4, from our Sierra College Elementary Statistics Student Survey to construct a percentage distribution table and describe the result. So here we're asked to construct a percentage distribution table. That is, we'll produce a table displaying all the data along with the associated percentages. And after we've constructed this table, we then need to describe the result. So, the first column in the distribution table needs to list the data. In this case, the data was, what is your age? So we'll label that column age. And then the data was the result of a random sample. And this raw data is in random order. So in the tables, we take the time to organize and display the data in a convenient way, which would be in numerical order. So we need to identify the minimum data value. The minimum data value belongs to the first row of the table. So looking through the data, we can see that the 17-year-old student was the youngest. So 17 belongs to the first row. The maximum data value belongs to the last row of the table. So searching through the data, we see that the maximum age or oldest student was 53 years old. So the 53-year-old student belongs to the last row of the table. So now, if we were to do like we did in the previous example and list every age from 17 to 53 individually, the table would be 37 rows long. This is too many rows for a reasonable distribution table. In this case, the data values need to be grouped. There is no single acceptable solution for grouping the data values. As long as the selected grouping produces a table that clearly reveals the distribution of the data, that solution is considered acceptable. There are several factors to consider when deciding on how to group the data values. For instance, the first row must contain, not necessarily start at, the minimum data value. Also, the last row must contain, not necessarily end at, the maximum data value. And the scale should be consistent throughout the table. That is, the size of the increment from row to row should be the same. In addition, the resulting distribution table should not have too few nor too many rows. In general, tables containing anywhere from 4 to 24 rows are reasonable. Finally, each and every data value must belong to one and only one of the groups in the table. Following these guidelines when constructing distribution tables will help you produce useful and informative results. So, several things need to be considered in order to determine the best way of grouping the data in our distribution table. In this case, in order to span the range from the youngest student to the oldest student over a reasonable number of rows, let's say 8, in this table the scale would need to be about 53, which is the maximum data value, minus 17, the minimum data value. This gives us the 36-year spread, divided equally amongst the 8 rows that we'd like to include in our table, gives a scale of about 4.5. But counting or grouping ages 4.5 years at a time isn't very convenient. So rounding this result to 5 would produce a more practical scale. The first group could start at the minimum data value, which was 17, but doing so is not required. Since it was decided to use a scale of 5 in this table, it would be advantageous to begin the first group at a multiple of 5 just preceding the minimum data value. So the minimum age was 17, and the multiple of 5 just preceding 17 would be 15. So we'll start the first row in the table at 15. And then because we're using a scale of 5 in this table, we increment age groups by 5. So starting the first group at 15 and counting by 5s, we get 20, 25, 30, 35, 40, 45, 50 as we complete the table. Also, we have to make sure that each and every data value is included in the table and that each data value belongs to one and only one of the groups. So when the second group, age group, starts at 20, the first age group needs to end just before the age group of 20. in this case 19. And so the rest of the table is completed the same way. If the next group starts at 25, then the group before it needs to end before that, so that 24 would be the ending of the second group. This ensures that each data value belongs to one and only one of the groups. Also, using a scale of 5 means we just count by 5s. So from 19 to 24 we count by 5s, 24 plus 5 is 29, and so on, counting by 5s. 34, 39, 44, 49, 54. So here is the decision that we'll use to group the ages for this table. Now we need to develop the frequencies. So to do this, we go through all the data and count who belongs to which group. The first student was a 20-year-old student, and the 20-year-old student belongs to the 20 to 24-year-old age group. The second student in the sample was 19-year-old, and the 19-year-old belongs in the first group, the 15 to 19-year-olds. The third student in the survey was 21, and 21-year-old students belong to the 20 to 24 age group. Here's another 21-year-old, and another 21-year-old. And the next student was 20. They belong to the 20 to 24-year-old age group. The 20-year-old student also belongs to the 20 to 24-year-old age group. The 53-year-old student belongs to the last group, the 50 to 54-year-old age range. So it gets counted there. 20-year-old students belong to the 20 to 24-year-old age group. 22-year-olds belong to the same 20 to 24-year-old age group. The 38-year-old student is counted in the 35 to 39 age range. The 40-year-old student belongs to the 40 to 44 age group. 18-year-olds belong to the 15 to 19, and so on. So each and every data value is then counted in each of its, in this case, age groupings, as we go through the entire set of data. So again, the 20-year-old students belong to the 20 to 24-year-old age range. The 34-year-old student is counted in the 30 to 34-year-old age range. 17-year-old students belong to the 15 to 19 age group. And finally, the 22-year-old student belongs to the 20 to 24 age group. Now, the frequency is just the count of all these data values. So if we go through and count how many students were 15 to 19 years of age, we would find there was 1, 2, 3, 4, 5, 6, 7, 8, 9, giving a frequency of 9 for the 15 to 19-year-old age range. Counting the number of students who were 20 to 24 years of age, we find 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, a frequency of 26. The 25 to 29-year-old age groups has a frequency of 4. 1, 2, 3, 4. There was only one student who was 30 to 34 years of age, and one student who was 35 to 39-year-old. 2 students fit the 40 to 44-year-old age range. And if you look at our tallies, there was no students in this sample at all that were 45 to 49 years of age. So the frequency would be 0, indicating that no students fit that age range. And finally, the oldest, last student, there was just one that was in the 50 to 54-year-old age group. So to check this work, if we sum or add up all the frequencies, all of the frequencies sum up to the total sample size. In this case, 44. Now, the table we were asked to construct is not a frequency distribution table, but a percentage distribution table. So we need to convert these frequencies into percentages by taking the frequency and dividing by the total sample size, and then multiplying by 100% to convert it to a percentage. So for the 15 to 19-year-old age group, the percentage is found by taking the frequency of 9, dividing by the sample size, 44, multiplying by 100, we get 20.4545%. And rounding percentages off to the nearest tenth of a percent, we would get 20.5%. For the percentage of 20 to 24-year-olds in our sample, we would take the frequency, which was 26, divide by the total sample size, 44, multiply by 100%, gives us 59.0909%. Again, rounding off to the nearest tenth of a percent, we would get a result of 59.1%. To find the percentage of 25 to 29-year-olds, you would take the frequency, which was 4, divide by the total sample size, 44, multiply by 100, you get 9.0909%. When rounding off to the nearest tenth of a percent, we would get 9.1%. The percentage of 30 to 34-year-olds is found by taking its frequency, which was 1 student out of a total of 44 students, times 100% equals 2.2727%. Rounding this result to the nearest tenth of a percent gives us 2.3%. The same result is seen in the 35 to 39-year-old age range. There was just one student in that age group out of a total of 44, times 100% gives you 2.2727%, or 2.3%. The percentage of 40 to 44-year-olds in the survey had a frequency of 2, divide that by 44, times the 100% gives us 4.5454%, which when rounded off to a nearest tenth of a percent is 4.5%. 0 or no students were in the 45 to 49-year-old age range. That gives us a percentage of 0%, or 0.0 to show the extra decimal place. And the percentage of 50 to 54-year-old students in the sample, there was just one. Divide by the total, 44, times the 100% gives us 2.2727%, which rounds off to 2.3%. Here, if we were to sum all the percentages in the table, it should equal the 100%. But if we take the time to do so, you'll see that it actually adds up to 100.1%, indicating that an error was made. So we should go back and check our work. But I was certain that we did everything correctly and that we rounded off everything correctly. So in this instance, the 100.1% error that we see is actually due to round off error. So this is why we carry the extra decimal places in order to help minimize this round off error. Because when you take a result and round it off, it's no longer exact. And then when you have many results which have been rounded off, sometimes the round off error accumulates big enough for you to see. So in this case, the error is not due to anything that we did wrong, it's just due to round off error. And those are the things that sometimes happen. So now we can include the percentage in our distribution table, and we get the following result. But our distribution table is not complete until we have a title. And the title needs to convey both the data, in this case, which is age, and the population we sampled from, which was Sierra College statistics students. So an appropriate title for this type of data would be Age of Sierra College Elementary Statistics Students. So here we've completed the percentage distribution table for ages of Sierra College Elementary Statistics students. Now we need to describe our results. To describe our results, we just need to use words to report the results that can be directly derived from the data. Here we see that the overwhelming majority of students, 59.1%, were in the 20 to 24-year-old age group. This was followed by a 20.5% of students falling in the 15 to 19-year-old group. And then 9.1% of the students were 25 to 29 years of age. We also had students ranging in age from the 30 to 54-year-old age range, but we only had one or two in each of those groups. So we can come up with one description using these words. The majority, 59.1% of Sierra College Elementary Statistics students surveyed were 20 to 24 years old. About 20.5% were around 15 to 19 years old, while just under half that much, 9.1%, were 25 to 29 years old. There were students that ranged in age from about 30 to nearly 54 years old, but this older age group only made up 11.4% of this sample. This description is accurate and perfectly fine to give, but you notice it is quite convoluted and maybe difficult to follow. If we were to turn to the language of statistics, we might come up with a better way of describing this result. In the language of statistics, distributions that are asymmetric, that is, not symmetric or lopsided, are called skewed. The ages of Sierra College elementary statistics students is skewed, that is, asymmetric, because the majority of students were 20 to 24. Students younger than 20 were only younger by a few years, but students older than 24 were older by several years. When the data values extend much further in the increasing or positive direction than the decreasing or negative direction, the distribution is said to be positively skewed. On the other hand, when the data values extend much further in the decreasing or negative direction than the increasing or positive direction, the distribution is said to be negatively skewed. In this example, the age of Sierra College elementary statistics students extends much further in the older or increasing direction, thus making the age of elementary statistics students at Sierra College positively skewed. Thus, we can make a much clearer and concise description by saying, the age of Sierra College elementary statistics students has a positively skewed shape distribution.